whenever I think of FPGAs, for as long as I can remember, I always thought of Xilinx. And that's what my professor at university also taught. But now I can, get to hear from Ken O'Brien, the C2 at Xilinx, and certainly we've been using FPGAs in HPC in different parts of it. But I'd like to know they're down the road. Without further ado, go ahead, Ken.
Screen
is yours.
Thank you. You can hear me okay? Okay. Hello, my name is Ken O'Brien. I'm actually a senior research scientist at Xilinx. I'm not the CTO. In this talk, I'll cover a spectrum of architectures that have emerged to address the demands of compute and memory requirements of modern applications. I'll talk about how specialization of hardware architecture is critical to achieving the performance scaling, and this applies to many domains, including HPC, ML, and others. I'll give two examples of hardware customizations that we do on FPGAs, like spatial processing and custom arithmetic. And using a network intrusion detection system example, I'll demonstrate the benefits of these approaches. So before I begin, a little bit about our group. So I'm part of the Xilinx Research Lab in Dublin. We're part of the Global CTO Office. We're 10 researchers. We have a very active internship program. We're the applications group, and we work mainly on building systems. We do architectural exploration to figure out how to best express solutions on FPGA from the domains that we're looking at. And most recently, we've, in the last few years, have been looking at quantifying the value of our devices in ML. We collaborate within the company with the engineering group, but also externally with many academics in universities and external commercial partners. Okay, so what are FPGAs? We can think of FPGAs as the chameleon among semiconductors. You can customize all aspects of the design, from the interfaces, the I/O interfaces, compute architecture, and even the memory subsystem. You can tailor all of this to the application. And the use case is you require maximum speed and efficiency, but you want to avoid going through the process of building a chip. You don't want to go to a foundry and produce a chip for your application. Something may change in the future, but with FPGAs, you can always reconfigure. So looking under the hood, what are FPGAs? What are they made of? FPGAs are made of lookup tables, on the order of millions of lookup tables, and they're connected through a programmable interconnect. So when you program an FPGA, it configures all of these lookup tables to express a circuit that describes the design that you've built. The lookup tables are surrounded by programmable I/O, and this allows you to reach out to memory, like HBM or DDR, but also to reach out to PCIe to talk to the host. Within the FPGA, there's also DSP blocks, which are specialized components that allow the FPGA to efficiently execute operations to do with the DSP domain, but they're more broadly useful in that they implement n-bit multiply accumulate instructions, so there's a wide variety of applications that can benefit from them. There's also SRAM. This is high bandwidth on-memory chip that you can utilize on the FPGA to construct custom memory hierarchies, custom caches specific to your application. When you combine multiple dies using a silicon interposer, you create superlogic regions. You combine these, you have a full FPGA device. So some context. Looking at a megatrend, the machine learning domain, we're seeing rising compute and memory requirements. And since 2012, we've seen doubling of these requirements every 3 or so months. This is driven largely by large neural networks with many billions of parameters, like the Turing NLG or the GPT-3, with, in that case, 175 billion parameters. And the machine learning domain in general is quite compute intensive, and it seems to be continuing in that trend. There's some challenges in the semiconductor industry for keeping up with these requirements. So there's manufacturing difficulties going down below 5 nanometer transistors. There's rising energy densities, so shrinking the transistors and dissipating the heat is becoming an issue. The design costs, so the price per square millimeter on the chip is rising. And we're seeing limited, this is across the board, all transistor-based technology, limited performance and power benefits going to smaller technology nodes. So what we're seeing here can be summed up by hitting the physical limits of silicon-based computing. And with that, we're seeing a move away from standard Van Neumann architectures, and this is where architectural innovation is becoming paramount. So in the past few years, we've seen an explosion in a variety of different architectures, largely driven by the race in AI for maximum performance or power efficiency. And we've seen this across all levels, from very low power embedded devices all the way to desktop accelerators and data center devices as well. And within these devices, the trend is that performance scalability is achieved by customizing the operations and the memory. Sparsity is being exploited in the memories and compute systems. We're also seeing custom numerical representation. Some people are exploring posits as a representation for their numerics, and we're also seeing customized ALUs and data flow architectures. So very wide spectrum of devices, largely driven by the AI trend. So let's have a look at some innovative and customized compute architectures. So if we think about accelerators on an FPGA, we can go in one of two directions. So we can go and make generic accelerators that are broadly applicable to a wide number of solutions, or we can go to the right of this diagram and co-design the hardware to our application, and then we can have specialized, faster, and more efficient solutions. So if I start on the left and consider a deep neural network example, if we were to take this approach, could be summed up by a matrix of processing engines. So in this example, a matrix of processing engines on an FPGA would be used to execute a neural network layer by layer, and your performance is achieved by batching the inputs. And this kind of approach is good for customizing for machine learning in general, because you're essentially building a matrix of processing engines that can execute operations that are broadly applicable to many different kinds of layers of neural networks. And you specialize the processing engines by specializing the operators or the ALU types, so that they operate on tensor, matrix, or vector-based data types. So on this example, you would batch the inputs, and then you would process layer by layer of the neural network. So in the next, so in that example, still you would achieve specialization by implementing the common operations within your compute device. You would support only the precisions that you need to execute, and you may have a permutation network to best shuffle the data around. And if you wanted to increase performance, you would replicate the processing elements. So if we went in the other direction and we went to spatial processors, which is definitely an FPGA-specific approach, what we would do here is we would take the entire neural network and we would map it to the fabric of the FPGA. So every neural network layer would have a corresponding piece of hardware in the FPGA. All of the weights would be, you would need to access them in parallel, because we would execute all layers in parallel. And you would customize the entire CNN design to the FPGA. The benefits being increased efficiency and low fixed latency, and this is something that we do on FPGAs. Okay, so from a point of view of getting performance, you would allocate resources proportional to the compute requirement of the layer. So for each layer, if you have a layer that has a large number of arithmetic operations required, you would allocate more FPGA logic to increase the parallelism of that layer, and then you would have all layers throughout the network basically outputting at the same speed as they feed into each other. And when that occurs, you can stream the inputs in and stream the outputs. So a little bit about performance scaling in this approach. So let's say we have some design and we've done a folding of 10, which means we've built a design such that we can accept a new input every 10 clock cycles, and we're getting 20 million requests per second, or whatever our performance metric might be. And let's say we want to target a smaller device, some kind of embedded device. So we'd be able to scale the design down. We would fold it such that we're able to take a new input every 1,000 clock cycles, but we're going a little bit slower at 200,000 requests per second. But the benefit is we can go to a smaller device with a smaller power footprint, and you could imagine deploying these on the edge as an embedded device. Let's take the same design, go the opposite direction, and scale up to maximize the throughput. And in this case, we have no folding, so we're able to take an input every clock cycle, and we're able to get maximum performance of 200 million requests per second. So the takeaway from this is that you can scale the performance and resources to meet the application need and the device that you are targeting. And if the resources allow, you can fully unfold the design and take an input every clock cycle. So another approach is customizing arithmetic. So if you're able to reduce the precision of the arithmetic that you're computing with, and customize it so that you're going to a reduced precision, it shrinks the hardware cost and you're able to scale the performance. So if you express your computation in a particular data type and you reduce the complexity of that, you reduce the area on the FPGA that you're occupying, therefore you can replicate more multipliers or more operations, and therefore you can scale. And an example that we've seen with an 8-bit weights, 8-bit activations neural network scaling down to a 1-bit weight, 1-bit activation with an RTL design, which is a low-level programming interface to FPGAs, we've seen a 70x speedup. And in the diagram you see for both RTL, which is a low-level programming interface for FPGAs, and HLS, which is a high-level interface for FPGAs, it's the same for both. You see a benefit by scaling down the complexity of the operations that you're executing. And there's also the potential to reduce the memory footprint and avoid a memory bottleneck. So these kinds of workloads, and many in HPC, are memory bound. And if you can reduce the minimum precision, you reduce the amount of data you need to move. And in the case of a DNN, you can maybe stay on chip, which has obvious performance benefits. And there's inherent power savings. So if you have a simpler operation, you're using less wiring, there's less switching, you have less energy costs on each operation. And on the right, we see a table where we have ResNet 50, 32-bit representation of 100 megabytes, scaled down to 1-bit. It's only taking 3. And we have tools that help you scale down the precision of neural networks. There is some retraining required, but as I said, there are tools to support with that. And last thing on customizing arithmetic, customizing the arithmetic within your designs. On the left, the matrix of processing engine approach, you're likely to have the same precision throughout all of the layers because you're reusing the same hardware. Whereas on the right, you can customize each layer, whether it be weights or activations or whatever you're processing. You can customize all aspects of the computation to whatever precision that makes sense for your application. So some results. Taking an example of a deep network intrusion detection system. So deep neural networks are increasingly popular for traffic classification. You get increased accuracy, and you can avoid the feature engineering phase of deploying these classifiers. They operate on a pass-fail policy, and they're trained on, in this example, a data set of synthetic and real attacks. So the requirements for this were 150 million requests per second on a 100 gigabit line. And if we compare both approaches, this matrix of processing engines, to a data flow approach, this is using the same network where we've retrained it using one of our tools called Brevitas. We've gone from 8-bit down to 2-bit. We've small drop in accuracy, but using a fully unrolled, fully unfolded design, we're able to get a 1000x improvement, and we're able to get a 1000x reduction in latency. So if we look at the resources, we see that the data flow approach, the spatial approach, gives you low resource footprint and a low clock rate. And overall, we get a 1000x improvement over Vitis AI. And Vitis AI is an example of one of these matrix of processing engines approaches. So at this point, you might be saying, okay, well, let's always spatialize our design, and let's go for the custom fully unrolled approach. And I would say, let's consider the spectrum again. If we go to the left with the matrix of processing engines, the generality is incredibly important. So with Vitis AI, the benefits that you get there is you can, because it's general, you can build frameworks on top, and Vitis AI is integrated with Caffe and other machine learning frameworks. And if you have new neural networks that are within these frameworks, you can take advantage of Vitis AI to deploy them. And yep, so Vitis AI is a good place to start because you've got a lot of the work done for you. And if you meet your needs there, if you consider what your requirements are, And while SAI gives you that, then you're done. But if you really want to go for the full performance, you can always build a custom design. So you really have to consider what your needs are. Okay, so summary. So I've talked about a spectrum of the architectures that have emerged given the requirements of the applications. We had a look at some of the customized architectures in the context of DNNs. This is also applicable to the HPC domain, as these are largely tensor-based or linear algebra-based operations. And we've seen how the specialization of hardware architectures are critical to scaling, given the issues in scaling to next technology nodes. And if you're working in the space, we'd love to hear from you. So please reach out. Just before I close and take questions, if you're an academic researcher and you're working in this space, you should be aware of the Xilinx Academic Compute Clusters, XACC. We have 4 centers around the world. They are free to use. And the idea is to build up research around these devices in high-performance computing. The hardware itself, this is an example from the ETH deployment in Switzerland. We have 5 servers, 10 FPGA nodes, and they're connected by a 100 gigabit switch. There's a link at the bottom. If you're interested, please reach out through that link. And thank you. I'll take questions. I'll leave that slide up so you can see the link. Otherwise, you can Google XCP XACC. Thank you.
So we have a question from Sahid about should we expect easier programming tools soon? Something to GPU.
Okay, so in the past, if you wanted to work with FPGAs, your only option many years ago was to do low-level programming. You would program the devices using an RTL language like Verilog or VHDL, and you had to consider things in terms of rising clock edges, wires, and gates. Since then, we've gone into the era of high-level synthesis, and you're able to program these devices using C++. And this has allowed people without a background in hardware design. So my background is in high-performance computing. I program these devices with C++, and the labs group in Ireland developed all of our proof of concepts in high-level synthesis. From a point of view of ease of use, there's also libraries being developed for common operations. So we're trying to raise that abstraction level so that it should be easier for newer people, especially people without a background in FPGAs, to access our devices. I'd say looking into the future, there's some, so the low-level interfaces using VHDL and Verilog are still very much in place, and the high-level synthesis approaches are also a product. But looking into the future, there's also research projects that we have in the lab to do with SYCL. So SYCL is a single-source API for programming heterogeneous systems. And if you're interested in interested in other ways to program FPGAs, maybe I think the SYCL project is an interesting research project as well.
That was very interesting, Ken. If you could maybe share a link in the chat on the SYCL project, that would be appreciated.
Yeah, sure.
I'll certainly follow up. I'm sure others have the thought. One last question. You mentioned C++. I wouldn't be surprised if somewhere you'll also get questions, will you support Python for FPGAs? So be prepared for that. Who knows?
People should look at the PINC project. So we have Python on Sync. So the PINC project is a way to program FPGAs from. Yeah. So if you're interested in programming FPGAs from the Python layer, there's libraries and there's an environment largely based around the Jupyter Notebook. If you're familiar with that, then that's a really good way to. Yeah. It's a great question. Thank you.
I spent more time with VHDL, so that's why I need to brush up on this, I suppose.
There's always HLS.
Yeah. Thank you, Ken. Very interesting. And my apologies. I thought you were the CTO, but even as a senior scientist, you did a great job. So I expect the title of CTO next to your name. So
thank you very
looking
much.
for that.